In this video, we're going to practice problems related to a vehicle turning on a banked curve. This problem explores how the banking angle and friction allow a car to safely navigate a turn. To handle these problems, we generally need to understand two different scenarios. In the first scenario, imagine the vehicle is traveling at a low speed, or maybe the bank surface is sleek. In this situation, the car tends to slip down the bank, right? So in this case, you'll be finding the conditions needed to prevent that downward slide. Conversely, think about vehicle moving way too fast or at a very high speed. In this scenario, the car tends to fly away from the bank or attempt to slide up the bank. Consequently, here you will be looking for the conditions that stop the car from flying off the road. So to begin our analysis, we always start with the free body diagram. To work on the free body diagram, both scenarios start the same. The car always experiences the gravitational force Fg acting downward, the normal force Fn acting perpendicular to the road surface, right? But the big difference comes down to the friction force. We know that the friction always opposes the tendency of motion, right? If the car tends to slip down, friction points up, right? So this is the case when the car drives at low speed, the friction should point up the bank. But if the car tends to slide up or fly away, the friction should point down the bank, right? Now let's dive into our example to take a closer look at how we handle these two scenarios. Here we have a curve. The radius are 180 meters. The curve is ideally designed for a car traveling at 70 kilometers per hour. So V is 70 kilometers per hour with zero frictional forces. This first part, we need to find the angle. The road must be banked so that the car can make a turn safely. Because the surface is frictionless in our first part, our free body diagram is simple. Now let's draw the free body diagram here. It's the gravitational force Fg, and the other one is the normal force Fn. To analyze the forces, we need a coordinate system where one axis lines up with the acceleration. The acceleration here is the centripetal, which points horizontally to the center of the turn. So we can just use a standard horizontal x-axis and vertical y-axis as our coordinate system. You see that the normal force, Fn, is actually angled, right? So we must break it into its x component and y components. How do we do that? We create a right angle triangle, right, with two sides along the x-axis and y-axis. This is the x component, Fnx, and this vertical one is the y component, Fny. And this is the angle theta we are trying to solve. This is the angle theta. And this x component, Fnx, is the opposite side of the angle theta. So we have the opposite side, Fnx over Fn is equal to sine theta. This gives us Fnx equals to Fn sine theta. For the y component, Fny is the adjacent side of the angle theta. So Fny over Fn is cosine theta. This gives us Fny equals to Fn cosine theta. Okay, so we've got these two components of Fn. As soon as we have all forces along the x or y directions, we can find the net forces for each direction. In the vertical direction, we have F net along y direction equals to, we have this Fny and Fg, right? The net force in y direction is Fny minus Fg. So Fny is Fn cosine theta, and Fg is the product of mass and gravitational acceleration g. Now, because the car is not moving up or down, the acceleration or the net force in this vertical direction is actually 0. So if we rearrange this equation, we have mg equals to Fn cosine theta. Okay, in the horizontal direction, the only contributing force is Fnx. So we have the net force in x direction equals to Fnx because the car undergoes a uniform circular motion. So the net force in this horizontal direction is actually providing the necessary centripetal force, Fc, right? So this net force is actually equals to Fc, the centripetal force. So we have Fc equals to Fnx. By definition, the centripetal force Fc is equals to the mass multiplied by the v squared over r, which is the radius. Fnx is Fn sine theta. Right, now you see we have two equations. This is equation 1, this is equation 2. So if we divide equation 2 by equation 1, so on the left side we have mv squared over r, then divide by mg equals 2. And on the right side from equation 2, we have Fn sine theta over, from equation 1, we have Fn cosine theta. And right away, we can eliminate Fn and the mass m from both the top and bottom of the fraction. We know this sine theta over cosine theta is simply equal to tangent theta. So we arrive at our final equation, tangent theta equals to v squared over rg. Now let's plug in the values and solve for theta. We need to start by converting the speed of 70 km per hour into the meter per second. We do that by dividing by 3.6, which works out to approximately 19.44 meter per second. Okay, so we have V is 19.44 meter per second. Then we have a square over r is the radius, 180 meter, and g is 9.8 meter per square second. And that works out to about 0.214. To find theta, we take the arctangent of 0.214, which gives us an angle of approximately 12.1 degrees. So if the surface of the road is frictionless, it need to be banked at 12.1 degrees so that a car driving at 70 kilometers per hour can pass through that curve safely. Now, in reality, you can't expect all cars to drive at exactly 70 kilometers per hour when taking this curve. So what happens if a car drives slower, say at 30 kilometers per hour?